Today we are going to introduce another emerging non-volatile memory, that is this phase change memory, TCM. And this is the outline of today's lecture. First, we will have an overview of the phase change material, and then we talk about the principle of the phase change memory, and then we will address some issues with regard to the phase change memory current scaling, multi-level capability, reliability issues, and finally we will present some array level and chip level demonstrations. So first of all, the phase change material typically use the chalcogens that is in the group 6 in the periodic table. So chalcogens basically are the elements in the group 6 except oxygen. So like this SSETE. So basically sulfide, selenide, telluride based material are called the chalcogenide material. And the phase change material actually is not new. It has been used in other applications before, like shown on the right hand side. Especially in your CD, DVD, actually the disc you have is made of the phase change material. And here we use that for the electrically programmable memories, that is the phase change memory. And one of the most widely used phase change material is this so-called GST, germanium, antimony, telluride, and the composition ratio is typically 2 to 5. So this is the same class of materials as the recording media of the CD or DVD. So in the CD or the DVD, a laser is used to write or erase the data by heating the GST material on a disk. So basically, if you shine the laser to your disk, right, then you will create this heating, and then it will change the phase of that GST material between this amorphous state and the crystalline state. And as we discussed before, so this non-range ordered crystal structure is called the crystalline phase. This is crystalline phase. And then after the pure heating, then basically you melt the material, and then if you quickly remove your heat sources, then the material will remain in this so-called amorphous state. And then if you gradually heat up the amorphous state again, then the material can be reheated to this crystalline phase. So it's a reversible process, depending on the crystallization and the amorphization changes. But for the CD and DVD, so the trigger of the change is by the laser. And after you change the state, later in the readout of the CD and DVD is also based on the optical method. In that case, the crystalline phase and amorphous phase will have different refractive index. So if you shine a light, the refractive index will be different between the crystalline state and amorphous state. So optically, you can detect that region is crystalline or amorphous. So this is how you optically read out the data 1 and 0 by looking at the reflection. So basically, the write and the read operations of the CD or DVD are done by the optical method. So basically, this is the same material, but different readout mechanism for the CD and DVD. But for our semiconductor manufacturing, we want the electrical readout mechanism. So then this is a phase change memory we will discuss today. So here again, this is a principle of the phase change. And no matter it's optical or electrical readout, then what you need to do is to create the temperature profile in the material. In the right operation, you have to increase the temperature above this melting temperature, so the atoms can move around. And then if you do a quench process, then this region will remain in its amorphous state. And optically, the refractive index will change, and also electrically, the resistance will also change. And then you do the readout, either optically or electrically. And then if you want to switch back, then you apply some temperature profile that is in between this melting temperature and this is the crystallization temperature. Then you can gradually move the atoms around. So the atoms tend to move to the lowest energy position. That will be the ordered crystalline state. The atoms will find its lowest energy. That is the crystalline ordered state. So here, this is the resistivity change of the GST material depending on the temperature in the crystallization process. So if you gradually ramp up the temperature of the material, the resistivity will change gradually as a function of the temperature. And then typically above 200 C or 300 C, then the device can return to the crystalline state. So you start from the amorphous, and after the temperature ramp up, then you will get back to the crystalline state. So here we are interested in this electrically programmable phase change memory. Instead of using the laser beam, we use electrical current to generate the Joule heating. So we can change the temperature profile in the material to switch between the amorphous or the crystalline state. So basically high current, high temperature, that will result in the amorphous phase, and electrically it will be high resistance state, HRS. And if we use a medium current to gradually heat up the amorphous state, it will change to the crystalline state after some time, and this will return to the low resistance state. So when we read out, we use a small current or small voltage to sense the difference in the resistance. So that's the principle of the phase change memory. Any questions so far? Okay, so let's move to the details of the phase change memory operation. And typically, the phase change memory is made of this so-called mushroom structure, because this is like a mushroom. This is like a mushroom. So here we have a bottom electrode, but we have this extension region. It's like a plug for the wear, contact wear plug. This is made of metal. This functions as a heater. This is like a resistor. So basically provides the heating. It's like a heater. And then the phase change material here, in this case, like the GST, is deposited uniformly across the wafer. And then on the top, you will pattern the top electrode. And the active region of the switching will be somewhere here, because the heat will dissipate from this heater. So this region will go through this transition between the crystalline to the amorphous, or the vice versa. So let's look at some animations to show the transition. So let's start with the amorphous state, and then we do the, let's start with the crystalline state. Let's do the reset process. The crystalline state is no reason state, and then here we'll pass a current through the device. So here you pass the current. Of course, you apply voltage, and then current will flow. And then as the current flows, then this current goes through this heater, then it will generate the Joule heating, and the Joule heating will heat up this region. So this is like increase the temperature above the melting temperature. And after that, we need to quickly remove the heat source. So in this case, we quickly withdraw your current externally. So the melted region, this region, will remain amorphous state. The reason is that here you increase the temperature above the melting temperature, so atoms here, the GST, the three elements, tend to move around because it's more like a liquid in that case. And then if you quickly remove the temperature source, in this case the current, then those atoms will remain, will go through so-called quench process. So the atoms will not have enough time to find its optimal position, so it will remain where it is. So this will result in the amorphous state. And if you want to switch from the amorphous state to the crystalline state, this is like a set process. Then we apply the lower amplitude of the current through this region. Then gradually ramp up the temperature. So then you give some kinetic energy to the atoms. So the atoms now can move around a little bit. So the atoms tend to find their lowest energy position. And that will be the crystalline phase. And after the set process, then the device will go back to the crystalline phase. So here I just like to show some animations for the reset dynamics. So here are some simulations. This is the heater. This is like the plug. And then the heat will spread out to this GST region. This is a cross-sectional view of the device structure. So here then, as we ramp up the current, so now the current is 400 microamp, and then so this is animation, so you look at the change. So now it's 500 microamp, so current move to here, and then here you see the color represents the temperature will go up, and let's move on. For example, now this is like 800 microamp, so you see this high temperature region, and then this is reaching the reset condition. Now the temperature is high enough, and then if you quickly remove the current pulse, so this part, depending on the temperature, so the temperature higher than the melting temperature, then this region will change to the amorphous phase, while the other regions, the blue region, will remain the crystalline phase. So here you create a high resistance region between the top electrode and the bottom electrode through this heater. So the current will be reduced because this amorphous region has higher resistance. And then we can go through the set dynamics. This is to switch back from the amorphous to the crystalline phase. So in this case, we apply a low amplitude current pulse. And here we ramp up the current. So then as you increase the current, then there will be some current flow. And typically this is through some like a percolation path, so-called percolation. So there are some weak links through this amorphous region, because the amorphous region, is a kind of random configuration. So there must be some percolation path for the current to flow. And as the current flows, then the current will increase the temperature locally. That can heal the random atoms. So basically give some negative energy to the atoms to move around. Then the atoms tend to go to their lowest position, energy position. That is ordered phase change, ordered crystalline phase. So as we further apply this current, you need to apply for a longer time to give them enough time to heal the region. And after some time, then eventually this part can be recovered to the crystalline phase. So to summarize, the reset from the crystalline state to the amorphous state, this is like the reset. Let's say from the low-run state to the high-run state. We need to apply large current and also a short pulse. This requires the quench process. So the key is that you need to quickly ramp up the current or the temperature and then quickly remove that. So typically the pulse width is like less than 10 nanoseconds. And then on the other hand, if you want to do the set from the high-run state or the amorphous state to the crystalline state, then you need to use a slower and a medium level current to heal the amorphous region. And typically you need like 50 nanoseconds or even longer. And this involves the nucleation and the crystallization process. And typically the thermal time constant when the temperature ramp up and down is within a few nanoseconds. So you have to apply the pulse longer than this thermal time constant. It's like your RC delay. When you apply the current, the temperature may not immediately ramp up. It has to wait for some time constant. But this is typically a few nanoseconds. And here we can show some real data. This is the resistance as a function of the cell current. Also, it's called the programming curve. So in this example, let's look at the reset curve first. So here we need to, if you want to reset from the amorphous, from the crystalline to the amorphous state, so you have to increase the resistance will not change. This is as a function of the current. So you have to ramp up the current until here, like 350 microamp. Then you will see the resistance change. Because now this is like the critical current you need to pass to generate enough heat or make the temperature high enough. Then after that, then the resistance. If you further increase the current, then the, let's say, the animation, as you recall, the volume of the high temperature region will further increase. So you will get more and more region to be amorphous state. Then the resistance will keep increasing. And here actually people have done the so-called TEM and the electron diffraction pattern to look at the 3 points in this process. So initially, this is under the microscope cross-sectional view. So here the bottom tinitride is a heater, okay? And then this whole phase change map, this whole region is this GST, and it's in the crystalline phase. The reason it's in the crystalline phase is evidenced by this electron diffraction pattern. So here when you shine the electron into this material, and if the material is in the crystalline phase, that means the atoms are arranged in this ordered pattern. So when you basically you can think the light goes through this, then the light or the electron will be diffracted, but this diffraction pattern will reflect this crystal structure. So you see this like a dot, this like a bright dot in the diffraction pattern. This is evidence that the material is in the crystalline phase. But if you look at the other points in this curve, for example, if the device is fully reset, so if you shine the light through this region, then you won't see those like ordered diffraction pattern, because the atoms are random. So when you go through the light, not light, I mean electrons, so then the diffraction will be also random. So they will smooth out this ordered pattern. So you won't see it from the microscope. And if you compare this fully reset state and the partially reset state, the difference from the image, you can see that the volume of this amorphous region can be changed depending on the current. If you apply higher current, then you create a larger volume of the amorphous state. If you apply lower current, you create a smaller amorphous volume. And if you look at these characteristics, you may think of the multi-level state. You can play with the current amplitude to change the volume of this amorphous region. Therefore, you can get different resistance levels, right? Different resistance levels for the multi-level storage. So this is the reset curve, and then the set curve, if you start with the amorphous state, the red one, so as you increase the current, this is like all those points are measured after this kind of pulse. If you increase the current amplitude, then the resistance will gradually decrease. This is because it will go through this crystallization process. But again, you cannot make the current amplitude too large. If you make it too large, then it will go through the reset process again. So the resistance will go up. So you really need to play with the pulse shape. For the reset, you apply a large and short pulse for the reset. And for the set, you have to apply a lower amplitude but longer pulse. So the amplitude is very critical. If the set amplitude is too high, then it will go through the reset again. This is not what you want. And also, from the DC IV characteristics point of view, here this is like a DC IV. If you sweep the voltage and then measure the current. Or actually, in this case, it's a current-driven measurement. So you should say you inject, sweep the current, and then you measure the voltage across the device. So you have this kind of IV characteristics. So let's say if you start with amorphous state, then initially the current is low, and then after some critical current or critical voltage, it's like your threshold voltage. If you keep ramping up the current, then you will see a snapback. It's like an S shape. Snapback, S shape, snapback. And then you further increase the current. So the device will go through the set process by the DC. And after that, if you sweep the voltage again, then the device will follow this curve. So I would say that in the DC measurement, you can only do the set operation. You cannot do the reset. Why is that? Because in the reset, as we discussed, we need to go through this quench process. That means you have to remove the pulse or remove the current very quickly. And in the DC measurement, it's very slow. So you won't have this quench process in the DC switching. This is not really DC, it's so-called the quasi-DC. Quasi-DC sweep. So-called the quasi-DC sweep is that you ramp up the current or the voltage in this staircase-like pattern, right? So at each current or voltage level, you wait for some time. So this is so-called the quasi-DC sweep. So any questions so far? Okay, next we will discuss one challenge for the phase change memory, that is the current scaling. So phase change memory, you notice that the reset current is typically very high, as we show in the previous examples. You need like 300 microamp, 400 microamp to trigger the reset. So this is one of the most important issues of the phase change memory, because that current directly related to your power consumption during the write operation. Of course, we want low power. We need to reduce the reset current. So there are different strategies to reduce the current. First one, reduce the contact area. This is like a brute force. So basically, if you recall the like a mushroom structure, right? So then this is your heater. This is your phase change material, GST, and this is your top electrode. So this is active region. So this is the contact area here. If you shrink this area, then the volume that you need to switch will reduce. Therefore, you just need less current to melt this part if this diameter of this heater decrease. So the most straightforward way is to do a simple scaling. If you make your device smaller, let's say the contact size or the pitch or the diameter of the contact smaller, then you reduce the reset current. And the other strategy is to engineer the device structure to achieve the highest heating efficiency for certain current. So eventually we need some temperature here, but the temperature depends on how efficient you heat up this region and how much the heat is dissipated. You want to preserve the heat locally in this region, instead of allowing the heat to dissipate. If the heat easily dissipates, then it's very difficult to locally heat up this region. So you want to reduce the heat dissipation to surroundings. You want the heat to remain in that contact area. So you can play with some interface property of the GST and the electrode interface. So it's like electrical and thermal engineering to make the heat efficiency higher. So you don't need to pass large current. You can heat up more efficiently. So let's look at the first strategy. This is a simply scale this contact area. This is, for example, if this is a cylinder, like this plug is a cylinder, then this is like the area of that bottom surface or top surface of that cylinder. So that is the contact area. And here we show the reset current as a function of the contact area. Here is a nanometer square. And for example, here this is in milliamp, or let's say this is 1 milliamp, this is 750 micron, 500 micron, and so on. So you see that this is like a linear trend. If you decrease the contact area, the reset current linearly decrease. But still, this is, for example, here, this is like 250 micron. You look at the corresponding area, 500 nanometer. Actually, it's pretty small. This is 500 nanometer square. That means about like 20 by 20 is 400, right? Maybe 22 by 22 or 23 by 23. So roughly, let's say 20 nanometer by 20 nanometer, roughly speaking, you still need like 250 micron. And 20 by 20 is a small number already, right? So even if you scale to 20 by 20 nanometer dimension, you may still need like 200 micron. And 200 micron is a large current, right? If you have a sense of the current, one transistor, as we discussed before, if the logic transistor W over L equals to 1, then typically one transistor can give you only like 20 or 30 micron in its on state. Then you have to size up the W over L to drive this phase change memory cell. So this is a big problem. And the other way to reduce the required reset current is to do the cell structure engineering thermally. So here, this is the structure A, is what we discussed so far is the typical mushroom structure. But this one, the GST material is deposited everywhere, and then you rely on this heater locally heat up this region. But you still have a lot of surroundings here, so the heat can dissipate. And a better way is to do this so-called confined cell. So structure A is a mushroom. Structure B is called confined. So the reason it's confined because here in this via, you deposit the GST. So heater is underneath. So when the heating happens, it will happen here, and then on the side, it will have the insulator, and the insulator is thermally also insulating. So heat will be confined in this part. So even past the same amount of current, the temperature of this confined cell can be higher. So that means you can apply less current to achieve the same temperature. So here on the right hand side, we show the reset current as a function of the contact area. And again, for the structure B, this confined cell, you can reduce the current typically by like 2x here. So as we discussed before, like this 20 by 20 is like 400 nanometer square, right? 20 by 20. Previously, you need 250 micron. If you do this confined cell, probably you only need this, half of that is like 100 micron or so. If you do this confined structure by thermal engineering. Okay, the confined cell will be a little bit more complex in the fabrication. You have to fill in this small dimension with the GST. So here are some examples. This, I believe, from Samsung. It demonstrated a very small confined volume for the phase change. So here, in this case, the phase change is in this red volume. So it's confined in this, and also this is the image from the microscope. So I believe this side is like a 17 nanometer. The other side is only 7.5 nanometer. So, and the height is, you can see this part is also probably only like 20 nanometer also. The height is like 20 nanometer. So the total volume, you can see, right, this is the cube, then it's 20 by 17 by 7.5 nanometer. So it's pretty small volume. You just need to heat up that volume. So then the volume reduction will help with the current. And then the researchers have done some very smart experiments to look at the limits of the current in the phase change memory. So what would be the lower limit? So here this is already small, the volume, like 20 by 17 by 7.5. But I believe still you may need like tens of micron or close to 100 micron in this case. So then what is the limit for the current? And here the researchers from Stanford, I believe, use this carbon nanotube as electrode to look at the lowest current. The reason is that in this experiment, they use a carbon nanotube. You know, it's a carbon nanotube made of the carbon atoms, and it's a tube. But basically, it's a electrode. The carbon nanotube can conduct the current, and then they burn out this carbon nanotube to create this nano gap in the middle. And the nanotube, the diameter is very small. The diameter is only like 1 to 2 nanometer. So if you look at the schematic, so basically you pass, and then it deposits the GST, cover this part. So it's like they create manually, artificially, create a very small volume of the phase change memory cell, and this is determined by the carbon nanotube diameter. In this case, it's about only 2 nanometer or so. So this is like 2 nanometer by 2 nanometer by 2 nanometer. This is like a smallest volume you can think of. The reason they use carbon nanotube is because this volume is beyond any reach of the lithography, right? We have so far. Even with the EUV, you cannot make like 2 nanometer by 2 nanometer by 2 nanometer features on the chip. So this is just a scientific experiment to artificially use a carbon nanotube as the electrode. So anyway, so then the result on the right hand side shows that the current, reset current can be reduced to 1 microamp. So this is the lowest reported current to switch the phase change memory. So here we show the programming curve, and with this carbon nanotube electrode, typically the reset current will be below this 5 micron, and the diameter of the carbon nanotube is less than 3 nanometer. And you can switch the devices for many cycles in this experiment. And if you calculate the programming energy that is the voltage times the current times the pulse width, then it's like 100 femtojoule per bit to program 1 bit. This is the lowest number reported so far, but of course this is only good for this scientific study. It's not good for volume manufacturing because in the real chip you cannot use carbon nanotube as electrode. You still need to use regular lithography to define the electrode. But it gives you a hope. So here this is the summary of the scaling trend of the current, programming current for the reset. This reset needs higher current, the phase change memory. And if you convert that to the equivalent contact diameter, so this is like a 100 micron, 10 micron, and 1 micron. And this star is what we discussed in the previous slide, reached by the carbon nanotube electrode. If you can make the contact diameter like 2 or 3 nanometer, you can get down to close to 1 micron. But you know, today's lithography, the smallest you can do is like 10 or 15, around that range, right? Even for, as I discussed, the 5 nanometer process, 7 nanometer process, 5 nanometer process, there's nothing on the chip is 5 nanometer or 7 nanometer. Still, the smallest feature size on the chip is like more than 10 nanometer, maybe 14 or 15 nanometer also. So today, the best you can do is still somewhere here. So you still need to have like 60 or close to 100 micron for the phase change memory. So still the power consumption is a concern for today's phase change memory. If you, for example, as we discussed before, if the diameter is 20 by 20, even with a confined cell, this is like 20 by 20. You may need like 100 micron. So there's still a long way to go for the phase change memory. This will rely on the scaling. Any questions? Yeah? For the mushroom structure, your question is we reduce what, this part? You mean this one? Yeah. Okay, the mushroom structure, because to make the fabrication easier. So basically you make a pattern, different cell, right? So different cell, you make different contact wear, and then they deposit the GST uniformly across the wafer. So this way is everywhere. You just deposit a thin film, and then on the top you make a pattern, top electrode. This is easy for fabrication. So this GST needs to be deposited everywhere. You mean this distance? Oh, this is not good. We will discuss that in a minute. This will create the thermal crosstalk. So we will discuss that in the next. And then multi-level capability. Okay. So already mentioned that in the programming curve, you look at this resistance change, probably from the very off state to very on state, you can change more than 100 times in the resistance. Therefore, you can manually create the resistance levels in between. So in this intermediate state, then you can get multi-level storage, like 2 bit per cell or 3 bit per cell. So here you have different ways to achieve that. You can rely on either the reset side or the set side. This is a reset. This is a set. So basically you need gradual reset or gradual set. And if you do gradual reset, So basically here in the gradual reset, let's say this is a gradual reset. For example, this one, gradual reset, this part. You design your pulse width, pulse amplitude to different amplitude. And here, as we shown earlier, if you increase the reset current, then you will generate different volumes of this amorphous region. Therefore, you can increase the resistance from DCBA, right? So as you increase the reset current, DCBA. So this is the reset pulse amplitude to control. And in the set part, also if you can increase, this one is more abrupt, but if the device shown like gradual set part, you can also design the set pulse amplitude to create more percolation paths or smaller percolation paths. Therefore, you can get multi-level on this side as well. And also in the, I believe in the set part, in the reset part, you can play with this falling time. When you design the shape of the pulse, you can make the falling more abrupt or less abrupt. Therefore, if it's less abrupt, then you won't melt all the volume. Still, there are some like islands remain in the crystalline phase. Because as we said earlier, if you want to make it completely amorphous, you need to quench very quickly. But you can play with this ramp down rate of the pulse to design the quench rate. So there are different strategies to make this multi-level. But I would say in most of the demonstrations, the gradual set is more widely used. Because this is a gentle process, you can make it slowly to recover the amorphous region, so it's more controllable. While in the reset process, because you have to play with this melting process, so it's hard to control in some cases. So anyway, so you do have different mechanisms to achieve the multi-level. And here are some real examples. If you use the gradual set part, then you can get those 2 bits per cell. This is by applying a single set pulse with different amplitudes and get 4 levels of the resistance. And then on the reset side, you can also with different reset pulse amplitude and then get the 4 levels. But here you do see there are like variations, right? Variations. So it's a distribution. And you need to care about the overlap between the tails. So if the distribution is broad, then we need to do this write and verify. Similarly as in the land flash, you have to do the write and then you verify whether you achieve your target or not. If not, then you need to write again. So write and verify, right? So this is a loop. So first you apply a programming pulse, and then you check the resistance, whether it meets your target or not. If not, then you will reapply the pulse, maybe with different amplitude or different, in this case, falling rate. But anyway, so here are some examples. On the bottom left figure, it shows 16 levels can be achieved by this write and verify. So this means 4 bits per cell, right? In this phase change, 4 bits per cell. And also on the right hand side, it shows the improvement by the write and verify. So basically this is a CDF cumulative distribution plot. And then you want this to be very tight, very vertical. But initially you do have some distribution. But with verify, then you try to tighten that to make it very distinct, like 4 vertical lines, the CDF plot. So basically, the phase-changing memory is capable of this multi-level states, but you have to play with the pulse shape, and also you may have to use write and verify to tighten the distribution of the resistance. And next, let's discuss about the reliability issues. So this is non-volatile memory. Again, then it will suffer from this retention, right? So at higher temperature, typically higher temperature, it will trigger this spontaneous crystallization process. If you are in the amorphous state, if you bake your sample in 100 degrees C or 200 degrees C, then it will go through this crystallization process. So that means the resistance will drop. By the way, I forgot to mention, the typical temperature for the crystallization, TG crystallization temperature, is like 200 C to 300 C. Typically 200 C. Let's say 200 C. And the melting temperature is like 400 to like 600 or 700. So you have to pay attention to those temperatures. Of course, in the real operations, you will not have like 400 C or 600 C. I mean, from the environment. But those temperatures are local by the Joule heating locally. But anyway, so if your environmental temperature goes up, then the device will go through this spontaneous crystallization process. That means the high resonance state will gradually become the low resonance state. And you can plot this Arrhenius plot, 1 over KT plot. And then here, this is just an example, right? So if you bake the device or bake the chip at different temperature, like 200 C, 210 C or 160 C, and then you measure the time to crystallization. So basically, the time to change from high resonance state to low resonance state, and then you can draw this extrapolation using this slope, and then you look at 10 years again. If you recall, this is a number for 10 years, 3 times 10 to the power 8 second. And if you do that, you see here, and you back calculate what is the temperature for this one. You first look at the KT, right, in the electron volts, and then you convert back. That is about 110 C. So that means this device can sustain the temperature 110 C for 10 years. So this is a spontaneous crystallization. And on the other hand, it will go through the drift process. So this is an opposite trend. So the drift of the phase-changing memory will increase the resistance. This happens even without temperature. I mean, at room temperature. Of course, if you increase the temperature, the drift may be speed up. So we will discuss that more details in the next. So first, this spontaneous crystallization, as we discussed. So we have this Arrhenius plot, 1 over KT plot, and then you can do this extrapolation. And you have done the homework, so you know what I'm talking about. So here, then you can do the extrapolation based on this 1 over KT plot. So this is the amorphous state becomes the crystalline state. And then resistance drift with time. So this is due to the relaxation of amorphous phase. So the detailed mechanisms actually still under debate, but it's believed that after the programming, the device will go through so-called structural relaxation. And the high resonance state is dominated by the so-called Pulver-Kiel conduction. So basically, the electrons go through the traps. And then if you if you recombine some of the traps, if some of the traps are recovered, that means you have less trap, less conduction, that's higher resistance. So basically, if from the device behavior point of view, what you will see is that right after the programming, then you can achieve your multi-level state, right, multi-level resistance. But then as time goes by, if you monitor the resistance, you will notice that the resistance will increase over time, even at room temperature, So this is a more obvious for the higher resistance region, which is amorphous state. So typically then the fitting is like this resistance is a function of initial resistance and then multiplied by the time and then some coefficient in the polynomial formula. So this will be a problem for the multi-level operations, right? As you can imagine here. And also here you see the time scale. If you initially program your resistance to be here, after 30 days, the resistance increases to here. So this will be a problem for the multi-level, right? Because multi-level, this is resistance. Then you already define the threshold between the levels, right? If this resistance drift over time, cross this reference, then you create error. So the drift is a major limitation for the multi-level operation in the phase change memory. But this drift is more predictable, I would say. If you characterize your device, then you can know this function, then you can predict. So sometimes you can adjust your reference accordingly to compensate for this effect. And the next challenge is this thermal crosstalk. And this will answer the question you raised earlier. Why not we make those two cells closer, right? If you make those two cells closer, then the thermal crosstalk will happen. That means when you program this cell, you do the reset, you apply large current. This temperature, right, this heat will dissipate, right, to the surroundings. The temperature profile gradually spread out. So the nearby cell will see that temperature. This cell will go through will be under the disturb mode, right? Then with the temperature, then you can partially program the cell, or the cell's resistance will be disturbed. So let's have an example here. If the programming pulse width is 100 nanoseconds, and if you keep doing programming for this cell for 10 to the power 9 cycles, so totally you accumulate 100 seconds total thermal disturbance time from this cell. So you keep doing this for 100 seconds. And for the neighboring cell, 100 seconds. Okay. So this is 10 to the power 9 cycles. It's 100 seconds. 100 seconds is 10 to the power 9 cycles. And then the other cell, if the other cell, say 210 degrees C temperature, the other cell will spontaneously crystallize, even if we initially start with the amorphous state. So that means here, if you do the programming as we discussed, you need to reach the melting temperature like 400 or 600, let's say 600 C. And the temperature will gradually decrease, right? If the adjacent cell is close by, then the adjacent cell may be 210 C, right? If the temperature profile, if this is 210 C. If this is 210 C, that means if you keep doing this for like 10 to the power 9 cycles, you accumulate 100 seconds total thermal stress on the adjacent cell. The adjacent cell, according to this plot, will flip. So this is the thermal crosstalk. And as you can imagine, if you make the cell closer, then you will see more spread of the temperature profile. And here on the right hand side, we show the normalized distance. Like this is the first cell, this cell, and then the distance, this is the second cell or the third cell. This is the first cell, second cell, third cell. This is the first, second, third. And in the temperature profile, and this is, I believe, this is 1000 C, this is like 600 C. And second cell may say this 300 C. Third cell may say this 200 C. So if you keep doing that, then the other cells will be disturbed. And this limits how close you can place those cells. And the more issues, endurance, right? For non-volatile memory, you have this cycling endurance failure. And you keep set and reset pulses, and then the device, for example here, can maintain the window, memory window, on and off. But after here 10 to power 9 cycles, there are different possibilities. One is called stuck at LRS or stuck at a set. So here this orange dot means that the resistance will be permanently fixed to the LRS, stuck at LRS. This is more common failure mode. This is typically the GST after so many cycles diffuse out to the into the adjacent materials next to your heater. So there is an intermix of the material. So you cannot achieve the amorphous state. And sometimes the device will stuck at this HRS. This is due to the dual heating. After so many cycles, you may create a void in that region. So here this is heater, this is a GST. But due to the thermal expansion, sometimes after so many cycles, here you have a void. Means nothing here. If you have nothing here, this is like open circuit, right? Then you stuck at the HRS current state due to the material adhesion. Then you may create this void. So both modes are possible in the phase change memory. But typically the endurance is about 10 to power 9 cycles. All right, any questions so far? And finally, we will discuss the array level integration and the chip. So here, there are different array configurations. The first one is 1T1R, as we discussed, 1T1R. This is like 1T1R array. And one transistor here, this cross-sectional view under the microscope at the drain. Then you have this heater, and then you have the GST and the top electrode. So you have this 1T1R. And here the transistor provides the set and reset current. That's why if your reset current is several hundreds of microamp, you have to size up the transistor width to provide this current. Therefore, your cell area will be limited by the transistor width, and you can, depending on the reset current, you may use larger transistor. Therefore, your cell area can be 40 or even larger f². So this is the 1T1R array, and you know this is like a NOR array or DRAM array, right? Because this is like a random access. And in the phase change memory, sometimes people use BJT as the transistor. So normally when we say 1T1R, right, transistor, by default, we think this is a MOSFET, okay? But if you recall in the older technology node, then the transistor could also be BJT. So like this BJT transistor, bipolar junction transistor, BJT. And similarly is 1T1R, but the only difference is this T is BJT. You may not have seen that in today's more advanced technology node. But BJT does have one advantage compared to MOSFET. That is, BJT has higher drive current at the same dimensions than MOSFET. So because the phase change memory, as we discussed, require very high current, right, hundreds of microamp, then BJT can provide this hundreds of microamp more easily than the MOSFET. If you have the same width of the BJT, then you have higher current. And BJT here, I show this BJT. If you recall what is BJT, it's a PNP, for example, PNP 3 junction, and like P plus NP. So this is like an emitter, base, selector. I don't know if today's undergrad semiconductor courses teach BJT or not. But here, basically you have those 3 layers, and then the N layer is like your gate. It's like the gate. And this is like your source. This is like your drain. But they don't call it a gate, source, or drain. They call it like a emitter, base, and connector. But anyway, so the point is that BJT has larger current. So here, this is the summary, right? BJT versus MOSFET. So BJT, you have this PNP junction, the bipolar junction, and then here better current drivability, so it may reach for the 6 to 8F square if you use BJT. And then MOSFET, of course, the larger cell size. And phase change memory, you can also do this cross-polar array. And phase change memory, because you can use unipolar operation, because you have the current, the same direction, right? Larger pulse for the reset, or smaller pulse for the set, but you pass the current one directional. That means you can use the PN diode. Right? PN junction, PN diode, you know, PN diode, IV. You just need to have the positive side. Therefore, you can use silicon PN diode as the selector. This is unique in the phase change because it only requires positive voltage to set and reset. It's the same voltage, the same polarity of the voltage, but different amplitude. So we can use silicon selector, and in this case, phase change memory plus the PN junction. So this was demonstrated by Samsung like 10 years ago. So this is a cross-polar array, and then they have the silicon diode here, PN junction, and then the phase change memory. So this is a cross-point 1S, or you can go 1D, 1R. Because it's a diode. And I believe this diode, the silicon is made by the epitaxial method. It's epi-silicon to make this diode. It's epi-silicon. But the challenge is that you can only do one layer because the silicon epitaxial process cannot be stacked to multi-tiers. You cannot do like multi-level or multi-tier 3D exponential array. You can only do 2D like this one layer 2D cross-point array with the epitaxial silicon, because you cannot do the epitaxial silicon on top of those metal wires. Episilicon is some silicon substrate to start with. So here is a history of the fixed-range memory development. Actually, fixed-range memory was one of the earliest emerging number-tile memories to be invested by the industry. Actually, it's earlier than others, like earlier than the STT-MRAM, earlier than RRAM, and earlier than the Faro. So back in early 2000, industry has already started the fixed-range memory development at 180 nanometer technology node. And then there are scaling of the fixed-range memory to 2011. Samsung, as I mentioned, reported this 20 nanometer feature size by this cross-point array. And also at the chip level demonstration. And in the following year, Samsung reported the 8 gigabit fixed-range memory chip, starting from like 180 nanometer down to 20 nanometer from the early 2000s to 2010. So let's look at this particular design from Samsung, 8 gigabit fixed-range memory. So again, this is a cross-point array, and each tile is 8 megabits, and it has 4,000 word lengths and 2,000 bit lengths as one. You can call it block, or you call it tile, and you have many of those as a partition. You can think it's a bank. So here then there are some parameters. The cell size, because the half pitch is 20, so then the cell size is 2F by 2F. It's about 40 by 40 nanometer. And then the total chip size is this number 9 by 6 millimeter square. And the power supply 1.8 volts, and they validate the temperature operation from negative 25C to 85C. And again, we are interested in 85C because this is maximum temperature they assumed in the operation. And then there are like 1 gigabit per bank, 8 banks. And then the set pulse width, the speed is about 150 nanoseconds. And I believe the reset is even faster, a little faster than that. And the interface is like 128 bit or even 256 bit in parallel. And then the total like chip level write bandwidth, like 40 megabyte per second. So this is comparable with the NAND flash. So read cycle time is like 120 nanoseconds. So I/O bandwidth here 800 megabit per second per pin. So it's actually quite competitive at that time. Of course, this is not so impressive today, but imagine 10 years ago, this is quite competitive with other like NAND flash at that time. But after 2012, situation has changed. Somehow Samsung ceased their development on the standalone fixed-range memory because this one was developed for the standalone memory, like 8 gigabits. It's not embedded. It's for the like NAND flash replacement, or you can think NOR flash replacement, if you will. And even though at the same year, Samsung reported an OTS selector, and we discussed selector in the previous lecture. So in this particular design, they use silicon diode, but if you want to do multi-tier, as we said, you cannot use silicon as a diode. So you need this OTS, this organic threshold switch selector, and Samsung reported that in 2012 IEDM. But after that, no news from Samsung. And then in 2015, Intel and Micron announced the 3DX point. This is what we discussed before. And make the commercial product since then. And even today, you can buy it from Intel's website, the Optane SSD, which is basically the 3DX point, which is basically the fixed-range memory, cross-point array, with the selector. And selector is OTS selector. But I would say Intel reported OTS selector earlier. Intel reported the OTS selector at IEDM conference 2009. But Intel didn't disclose the material for the OTS. Samsung actually disclosed OTS material in 2012. If I recall correctly, it's a very complex silicon, germanium, antimony, telluride, or maybe sometimes they have an arsenic there. So very complicated anyway. So then in 17 and 18, SK Hynix has some cross-point array demonstration with OTS at IEDM, but no volume production after that. And since 2018, the focus of phase-change memory has shifted to the embedded non-volatile memory pursued by foundry, such as ST Microelectronics and TSMC. ST Microelectronics is a foundry in Europe. It's jointly owned by Italy and France, I believe. So this is the recent situation for the phase-change memory. And by the way, IBM and Micronix also have a research team working on the field today, working on the OTS plus phase-change memory, but no volume production yet. So here, let's look at some of the recent embedded non-volatile memory demonstrations for embedded applications, and particularly for the automotive MCU microcontroller. And this is one of the major business of the ST Microelectronics, ST. So for the automotive, for the MCU, when you use that under the hood or above your engine of your car, then the non-volatile memory is to sustain very high temperature. It needs to be much reliable than your commercial grade product. You need to turn the temperature even up to 150 C in the automotive electronics. So anyway, so here in the IEDM 2020, ST reported the 28 nanometer FDSOI based phase-change memory. So it's a 28 nanometer process, and you have the FDSOI as a transistor, and it's 1T1R. So here are some images of the array. I will skip the details, but basically it's 1T1R. And one cell gives you this 0.019 micrometer square, so it's pretty small. And you can calculate what is F square. If you think F is 28 nanometer, then you can do that. And then it demonstrated the chip, 16 megabytes, and there are 4 banks, each is 4 megabytes. And then ST also have another version, which is the phase-change the MOSFET to the BJT. I think their newer demonstration is on the BJT based, still at 28 nanometer load, but it uses the BJT as the access transistor. And here are the a set and reset resistance or radial current distribution, and here are the endurance. You can get 10 to the power 7 cycles. So here is a summary of the recent demonstrations, and also TSMC has reported phase-change memory on their 40 nanometer process in IEDM 2019. So the target application is embedded non-volatile memory for the E-flash replacement, especially for the automotive applications. And then ST has 2 versions. One is 1T1R, the other one is one MOSFET 1R or one BJT 1R. And if you convert the cell size, you see the MOSFET version, you need a 46 F square. But if you use BJT, because higher drive current, can reduce the cell size to 24 F square. And here are other parameters. I will not go through the details. On-off ratio. And the red current still high. At 28 nanometer, you see the red current. The reset current, you need 200 to 300 microamp. And then endurance is typically 10 to the power 6 or 10 to the power 7. And it can reach 10 years at higher temperature, because for automotive, it's not 85 C. You need to guarantee and 150 C. Okay, so this is the final summary. And the phase change memory is one of the most mature emerging non-volatile memory in terms of manufacturability, as demonstrated by different companies. And for the standalone application, for the storage class memory, for example, and Intel and Micron has this 3DX point, and as we discussed earlier, Micron drops this, but Intel continues. And then the power consumption is a major challenge. And the reset current, as we discussed, even at 20 nanometer load, is still larger than 100 microamp. Multi-level cell is possible, and you can do that by aggressive write and verify. And recently, I believe there's a paper from IBM demonstrated 1,000 levels. That means 10 bit per cell by very fine-tuning of the resistance levels, was demonstrated by IBM recently. And the reliability issues needs attention. For example, drift and thermal crosstalk. Those are unique issues in the phase change memory. All right. Oh, sorry, it ran out of time. So let's stop here today.